So looking at continuity no longer at a point but an entire interval is what we're doing in this lesson, and I included this right here because the endpoints are probably on the closed interval. The endpoints, that's always kind of confused me a bit, but this will really help walk you through that. I also included this definition just because I wanted to be evil, and this is more what you'll see in college if you take an analysis class. This is technically what the definition of continuity really is, but we're not going to really think about that one. So let's just focus on the basics. Yes, what we've been doing so far is basic and easy compared to that. So it really means the same thing. Let's take a look at this one though. So over which intervals is G continuous? So we're going to look at each one, choose all that apply, right? So we got to look at each and every interval. So choosing all that apply from -6 to -1. Let's start with that one. So I'm going to start with -6 to -1. So from -6 to -1, do we see any types of discontinuity? Do we see a jump in here, or a removable, or a vertical asymptote? And no, we don't. Now, I wanted to go over the whole thing. What about right here, the very end of -1, it has a jump. So that's why I brought this in. That's usually where I was a little confused. So f is defined, so it's continuous on a closed interval if f is defined in every point on that interval. If f is continuous on every point except for the endpoint, see how it's open there, a and b. Then if the limit from the right equals f of a, and then the limit as x approaches a. So think about this. So let's just say here's our interval, right? Here's a. So f has to be defined on that interval. So if we have a closed interval like this, from a to b, basically as x values, we don't want to have an open point there. We don't want to have one of these open like this. That would not be good. It has to be defined on all points. So if it's not defined on there, that's not good. Then f has to be continuous for all the points inside of here except for the open endpoints, right? So it has to be continuous. Then think about the limit as x approaches right of f of a. So as we approach this from the right, it has to be the same as the function there. Same thing here, as we approach from the left, has to be the same. So as long as you have that, it's considered continuous on the interval. So let's go down here, and you can see from -6, this is technically a point here, you can see that it's continuous on the entire interval, and then the limit as we approach this right end from the left is equivalent to the actual function. So yeah, that works. That is okay. If it was open, like from -1 to 1, then it wouldn't be okay. It wouldn't be continuous because the limit, it's not defined at the ends, right? It needs to be defined at the ends is what that is saying there. So let's look at -1 to 1. Oh, that's actually our next one. So -1 to 1. So from -1 to 1, even though it's continuous on the inside, the endpoints do not exist. And so that's why this wouldn't be considered continuous. So that's going to be out. So A is in, but B is out. Let's look at this one. So from -2 to 0. From -2 to 0, everything seems to be good except look at right here. That is not good. You know, we want it to be continuous at 0 at that end, at the right end. You know, you can ignore the rest of this graph. Pretend it doesn't exist on that entire, you know, we're just zooming in or just thinking about -2 to 0. I wish I could just get rid of the rest of the graph, but I can't. So that right there caused the discontinuity at the end. So this one is out. Let's look at 1 to 5 though. From 1 to 5, there's an obvious issue right here. See that discontinuity there? So even though the ends are fine, there's technically a point on the curve, right? So even though these ends are fine, right in the middle it messes up. So that's out as well. So we're going to go with none of these. Let's do one more example. I picked this one because it kind of has these what we call a cusp at the end. So we're going to learn later it's not differentiable at that spot, but it's technically continuous because the point exists there and the limit is approaching that point. But let's go ahead and look at this. From 2 to 7, the first interval is from 2 to 7. So from 2 to 7, technically they have the endpoints there. And there's no issues with this. Even though it has that cusp, like I was saying earlier, we're going to find out it's not differentiable, but it does exist. The point exists there. The limit's approaching it. It is continuous. Everything's fine with that. You know, we're looking for if there was like an open point at that spot. That's the only thing that would mess it up if it was an open circle there, or if we had a jump. What about from -4 to 0? So from -4 to 0, we're good. Just, you know, double check those ends. So -4 would be right here, 0 would be right here. The endpoints are fine. They're not open. There's no sort of discontinuity in between. So we're good to go on that one. So we're going to pick both of these.